My plan for this video is to talk about the Schwarzschild metric as a solution of the Einstein equation, and to extend that solution to create models of stars and planets. So let me start by recalling the Schwarzschild metric. Written as a line element, it's ds squared equals minus 1 minus 2m over r dt squared plus 1 divided by 1 minus 2m over r times dr squared plus r squared d omega squared. And here I'm using the shorthand notation where d omega squared is d theta squared plus sine squared theta d phi squared. Now, in previous lectures, we used this metric to describe the geometry outside a static, spherically symmetric, non-rotating, and isolated body of mass m. So if the areal radius of the surface of this body is, say, capital R, then this metric is describing the region of space-time outside the surface. So for little r greater than big R. And for little r less than big R, the metric is something else. And that will be one of the goals of this lecture, is to explore the interior metric, the metric inside the matter, where the areal radius is less than the radius of the surface. Of course, we're free to consider a space-time that's described by this metric, by the Schwarzschild metric, for all r, not just r greater than some areal radius capital R. So consider the Schwarzschild space-time for all values of little r. And as you probably know, this describes a black hole. So in the next lecture, I'll talk about the Schwarzschild black hole in some detail, and I'll also discuss gravitational collapse. But for this lecture, I want to focus on the Schwarzschild metric and how it's obtained from the Einstein equations, and also indicate how we can extend the solution to the interior of a star or a planet or a body of mass m. Before I dive into the technical details, let me make a few comments about these qualifications, that the body should be static, spherical, isolated, and non-rotating. First of all, static is a technical term that actually describes the space-time itself. So, as we'll see, it tells us that the space-time has a particular type of killing vector field, so it's describing the space-time outside the body, not the body itself. In fact, we can have a body that's collapsing, undergoing gravitational collapse, and it's still true that the space-time outside that body is static, as described by the Schwarzschild metric. Now, spherical symmetry is an assumption that we place on both the body as well as the space-time outside the body, and it's a technical assumption that there are killing vector fields corresponding to rotations, or symmetries corresponding to rotations, just like the rotations of a sphere. Now, the assumptions that the body is isolated and non-rotating, these assumptions probably aren't needed, because after all, if the body is not isolated, say there's another body nearby, then it's going to distort the body so that it's no longer spherical. And similarly, if our body is rotating, then it's not going to be spherical. So these assumptions aren't needed from a technical standpoint. We're just going to assume that the body and the space-time outside the body are spherically symmetric, and we'll assume that the space-time outside the body is static. The body itself might not be static, it could be collapsing. Our starting point is the Einstein equation. So the Einstein tensor, big G mu nu, equals 8 pi times Newton's constant g over the speed of light to the fourth power times the stress energy momentum tensor T mu nu. So remember, G mu nu is built from the metric and its first and second derivatives. T mu nu is built from the matter fields and the metric. So loosely speaking, this equation determines the geometry, or the metric, for a given matter distribution T mu nu. In reality, the situation is more complicated than that because we also have to make sure that the matter equations of motion are satisfied. For example, if T mu nu is the electromagnetic stress energy momentum tensor, then we need to add to these equations the Maxwell's equations, and then altogether the full system of Einstein equations plus Maxwell's equations is solved for the metric and the electric and magnetic fields. But just looking at the Einstein equation alone, it's already very complicated. It's a system of 10 equations. They are second-order differential equations, second order because they're second derivatives of the metric in the Einstein tensor. And they're coupled equations, they're nonlinear. So it's not possible to solve these equations analytically for any realistic astrophysical situation. But we can solve them numerically, and there are groups of researchers around the world that maintain and build large computer codes to solve the Einstein equations plus matter equations. But what we can do is solve these equations analytically in highly idealized situations. And that's how solutions like the Schwarzschild metric are obtained. So what are the assumptions needed to derive the Schwarzschild solution? The first assumption is that space-time is stationary. Now, stationary means that the space-time admits a time-like Killing vector field. So let's call that Killing vector field K. And remember, the existence of a time-like Killing vector field means there's a time translation symmetry. The second assumption is that this Killing vector field K is what's called hypersurface orthogonal. Now, there are various ways of expressing what it means to be hypersurface orthogonal. One way is to say that K, written as a covector with an index down, is the gradient of a scalar, or it's proportional to the gradient of a scalar. So let's let S and T be scalar fields. So this is a gradient of a scalar, partial mu T, and this is a proportionality function. S and T are scalars. Now together, these two assumptions are equivalent to saying that the space-time is static. So static is a property of a space-time that has two parts. It says it's stationary, and the Killing vector field corresponding to that stationarity is hypersurface orthogonal. It is possible for a space-time to be stationary and not be static. So in other words, it can have a Killing vector field that's time-like, but not hypersurface orthogonal. The third assumption that we'll make is that the space-time is spherically symmetric. And this is also an assumption about Killing vector fields. It says that there are Killing vector fields corresponding to rotations, the rotations of a two-sphere. So now let's work through some of the consequences of these assumptions. If we have a static space-time, so it has a Killing vector field that's hypersurface orthogonal, then we have a scalar field capital T, and we can choose the scalar field to be one of the space-time coordinates. So let's do that. Let's choose this scalar field capital T to be a space-time coordinate. And in fact, let's call that coordinate little t. Another way to say this is that I'm going to choose one of my space-time coordinates little t to coincide with the surfaces of constant big T, where this big T is a scalar field. Now, an immediate consequence of this choice is that the Killing vector field, which could be written as S partial mu T, this partial mu T is the derivative with respect to the space-time coordinates of the scalar field capital T, so that's just delta mu T. So we see that K with a lower index has only one component non-zero, the first component, the T component. So T is one of our space-time coordinates. Let's let xi denote the other space-time coordinates. We'll call these the spatial coordinates. Now consider the spatial basis vectors d by dxi. Any coordinate basis vector points along the direction in which the other coordinates are constant. So in particular, these vectors point along the directions in which the coordinate t is constant. So these span the surface, the three-dimensional surface t equal constant. In other words, they point along directions in which t is constant. Now the components of these three basis vectors are delta mu I. Now let's take the inner product between our Killing vector field k and one of these basis vectors d by dxi. So that's k inner product with d by dxi. In terms of components, that's k sub mu delta mu I, but k sub mu is s delta mu t, then times delta mu I, and this of course is 0. So this tells us that the Killing vector field k is orthogonal to each of these spatial basis vectors. In other words, it's orthogonal to the t equal constant surfaces. And this is what's meant by saying that k is hypersurface orthogonal. Let me draw a picture. These are the t equal constant surfaces. And now these are the integral curves of the Killing vector field, k, and we know that the Killing vector field is orthogonal to the t equal constant slices. And on each one of these t equal constant slices we have spatial coordinates xi, but the relationship between the coordinates xi on one of these slices and another slice is not yet specified, and we have some freedom as to how to choose those spatial coordinates. So let's do it as follows. Let's choose our spatial coordinates however we like on this surface, however it's convenient, and then let's carry those same coordinate values along the Killing vector field. So we'll carry the coordinate labels, the xi's, along the integral curves of the Killing vector field k. So in other words, if this is the point with coordinates, spatial coordinates 1, 3, minus 2, then this is also given the coordinates 1, 3, minus 2. And likewise, this point has coordinates 1, 3, minus 2. And we'll do that along each one of these integral curves of k. We'll just carry those same spatial coordinate labels along. Now with this choice of spatial coordinates, the Killing vector field, the integral curves, lie along the curves of constant spatial coordinate values. So k lies along curves of constant xi, in other words, along the t coordinate lines. So that means that at each point in the space-time, the vector k is proportional to the basis vector d by dt. Or said another way, since this basis vector has components delta mu t, then k mu is proportional to delta mu t. And in fact, let's write this k mu as then some function f times delta mu t. So this f is a function on space-time, a scalar function. Now let's use once again the fact that k is hypersurface orthogonal. So that tells us that k, inner product with any of the spatial basis vectors, must vanish. So this can now be written as k upper mu, g mu nu, times the components of d by dxi, which are delta nu I. And inserting our result for k upper mu, we have f times delta mu t, g mu nu, delta nu I. This is just f times g t I. So now this function f should be non-zero. We assume that the Killing vector field is everywhere non-zero. So this tells us that these components of the metric are all zero. So g t I is equal to 0 in these coordinates. Next, let's write out explicitly the condition that k is a Killing vector field. So we have 0 is the Lie derivative of the metric g mu nu along the Killing vector field k, and this is, by the definition of the Lie derivative, k sigma partial sigma g mu nu plus g sigma nu partial mu k sigma plus g mu sigma partial nu k sigma. And now the only non-zero component of k is the t component, and its value is equal to f. So this first term is f times partial t of g mu nu. Then we have g t nu partial mu of f plus g mu t partial nu of f. Of course, this result equals 0 for any value of the free indices mu and nu. So let's pick mu equals I and nu equals j. Now this is g sub ti, or tj, which vanishes, as we showed above. Similarly, this always vanishes if mu is equal to I or j. So what we're left with is partial t gij is equal to 0. So the spatial components of the metric are all t independent. Now let's choose mu equal t and nu equals I. Then this term is gti, which vanishes, and here as well we have g sub ti, which vanishes. The only non-vanishing term is this one, so we have 0 equals g sub tt times partial I of f, and assuming gtt is non-zero, this tells us that f is independent of the spatial coordinates. And now let's set mu and nu both equal to t. What we find here is f times the time derivative of gtt. Let's just use a dot for time derivative. And here we have gtt times the time derivative of f. And here this is also gtt times the time derivative of f, so we'll just put a 2 in here. And that's equal to 0. This equation is not difficult to solve. We can rewrite this as gtt dot over gtt equals minus 2 times f dot over f, and then integrate. And what we find is that gtt is an integration constant c over f squared. But now this integration constant comes from integrating over t, and we can integrate this for each of the spatial coordinate values xi. So this is really a function of xi. So let's collect together our results. We found that for a static spacetime, we can always choose coordinates in which g, I, t, or gti vanishes. The Gij components of the metric are functions only of the spatial coordinates. Let me just call those x. The TT component of the metric can be written in the form of some function of the spatial coordinates x over f squared, where f is a function only of the time coordinate t. And then the space-time metric written as a line element will have the form c of x over f squared of t dt squared plus gij of x dxi dxj, and the killing vector field has only a t component, and that's f of t, comma 0, comma 0, comma 0. Now we can write the metric in a little bit nicer form by absorbing this function f into a redefinition of the time coordinate t. So in other words, let's define a new coordinate t new as the integral of dt over f of t. So that's equivalent to saying that dt new is equal to dt over f of t. And then this becomes ds squared equals some function of the spatial coordinates times dt new squared. And the rest of the metric is not affected by this change in t coordinates since it's independent of t. So instead of calling this coefficient c, let's just call it gtt, with the understanding that it's a function only of the spatial coordinates x. And let's also just write t in place of t new. So then the metric for the static spacetime can be written as ds squared equals gtt, which is a function only of the spatial coordinates, dt squared, plus gij, a function only of the spatial coordinates, dxi dxj. And the killing vector field in these coordinates is just 1, 0, 0, 0. So this is the general result for a static spacetime. If the spacetime is static, so it's stationary with a hypersurface orthogonal killing vector field, we can always choose coordinates so that the metric has this form. Now remember, we're not only assuming that our spacetime is static, but also that it's spherically symmetric. So I'm not going to go through all of the details, but if we assume spherical symmetry, we're assuming that there are killing vector fields corresponding to rotations, the rotations of a two-sphere. And we can show that it's always possible to choose coordinates, choose spatial coordinates in this case, r, theta, and phi, such that the spatial metric, this part of the metric, has the form grr dr squared plus r squared d omega squared, where again d omega squared is shorthand for d theta squared plus sine squared theta d phi squared. And grr is a function only of r, and also gtt is only a function of r. So if we assume spherical symmetry, then we can write, as well as static, then we can write our spacetime metric as gtt, a function of r, times dt squared, plus grr, a function of r, dr squared, plus r squared d omega squared. So this is the general form for a static spherically symmetric spacetime. Or said another way, if your spacetime is static and spherically symmetric, you can always find a coordinate system in which the metric takes this form. Now, in this highly idealized situation where we are assuming that the spacetime is static and spherically symmetric, we can try to solve the Einstein equations analytically. So the Einstein equation is Einstein tensor equals 8 pi times the stress energy momentum tensor, where I'm setting Newton's constant and the speed of light equal to 1. And let's start with the most simple case by assuming that the space-time is vacuum. In other words, we'll assume that there's no matter content. T mu nu is equal to 0. So we'll be solving G mu nu Einstein tensor equals 0, and the solution we find will be the Schwarzschild metric, which is the metric for a static spherically symmetric black hole. So to solve this, we simply need to compute the Einstein tensor for a metric of this form. And as always, I encourage you to use a computer algebra system to simplify the calculation. Otherwise, it takes a lot of effort. So what we find when we compute the Einstein tensor for our static spherically symmetric metric is GTT is minus the metric GTT over R squared GRR times R times GRR prime, where prime denotes derivative with respect to R, plus GRR squared minus GRR. The RR component of the Einstein tensor is 1 over R squared GTT times R GTT prime minus GRR GTT plus GTT. The theta-theta component of the Einstein tensor is minus R over 4 GRR squared GTT squared times 2 GTT squared GRR squared, that's GRR prime, plus R GRR GTT prime plus GTT times R GRR prime GTT prime minus 2 GRR times GTT prime plus R GTT double prime. And the phi component of the Einstein tensor is just equal to sine squared theta times the theta-theta component. So those two components are proportional to one another. And all of the other components of the Einstein tensor vanish. So all other big G mu nus vanish. Now let's set the Einstein tensor equal to 0, since we're looking for a vacuum solution of the Einstein equation. So GTT is 0, GRR is 0, G theta theta is 0, and if G theta theta equals 0, then G phi phi is automatically 0. And the rest of the components of the Einstein tensor are already 0. So we have these three equations, but now this looks like a problem because we have three ordinary differential equations, but just two unknown functions, namely GRR and GTT. But in fact, these three differential equations aren't independent. If you'll recall, the contracted Bianchi identity tells us that the Einstein tensor must satisfy del mu G mu nu equals 0. So let's write this out in detail. We have, just using the definition of the covariant derivative, this is partial mu G mu nu plus Christoffel symbols, gamma mu mu sigma G sigma nu plus gamma nu mu sigma G mu sigma. Now let's set the free index nu equal to R. So this nu becomes R, R, and this is R. Now one thing to notice about the Einstein tensor with lower indices, I wrote out the components explicitly above, is that this is diagonal. So all of the off-diagonal components of G lower mu nu are equal to 0. And because the metric itself is diagonal, that tells us that G upper mu nu is also diagonal. In fact, G upper RR is just proportional to G lower RR, G upper TT is proportional to G lower TT, and so forth. So now, this equation, then in the sum over mu, only R survives. So this is partial R, G RR, again because G upper mu nu is diagonal. This is G upper mu mu R, GRR, and this, we'll just leave it for now as G upper R mu sigma, G mu sigma. But now notice that the only non-zero components of G are the diagonal components. So this is just some linear combination of GTT, GRR, G theta theta, and G phi phi. So if GTT and GRR vanish, right, then also G upper TT and G upper RR vanish. So these terms are zero. And G theta theta and G phi phi are proportional to one another. So the only terms left in this expression are just proportional to G theta theta. So this tells us that G theta theta is automatically equal to 0 if GTT, GTT, and GRR are equal to 0. So if we go back to our expressions, our explicit expressions for the components of the Einstein tensor, if these two equations are satisfied, the GTT and GRR equations, then we don't have to worry about this equation. It's automatically satisfied. And you can verify that just directly by taking, you'll have to take certain combinations of these equations and derivatives of these equations, and you can show that this equation holds. So we just need to satisfy these two equations for the two unknown functions GRR and GTT. Let me rewrite these equations and drop those coefficients in the equations. So we have R GRR prime plus GRR squared minus GRR equals 0, and R GTT prime minus GRR GTT plus GTT equals 0. These equations aren't difficult to solve. You'll notice this first one only depends on GRR, and the solution is 1 over 1 minus an integration constant I'll call K divided by R. And now given this expression for GRR, we can solve this equation for GTT, and the result is GTT is equal to some integration constant, let me just call it C, times 1 minus K over R. So now the space-time metric can be written as GTT, that's C times 1 minus K over R times dt squared, plus GRR, 1 over 1 minus K over R times dr squared, plus r squared d omega squared. Now this looks a lot like the Schwarzschild metric, but we have this funny constant c out front. Now if this constant c is positive, then we can easily absorb it into a redefinition of the time coordinate t. So for example, we could define a new t coordinate that's equal to the square root of c times the old t coordinate. But we should pause for a moment and think about the sign of c. Now you might have noticed that from the beginning we said that the Killing vector field is time-like, but we never actually imposed that condition. So let's take a look at k dot k, the inner product of k with itself. Now in these coordinates, the Killing vector field is just 1, 0, 0, 0. So this is just GTT. Or for this solution, it's c times 1 minus k over r. So if k is a time-like Killing vector, then its inner product with itself should be negative. So this shows that in order for this to be negative, at least for large r, where this term is small, then we need c to be negative. we want C to be negative so that the killing vector field is time-like at large R. So let's set C equal to minus the magnitude of C and absorb the magnitude of C into a redefinition of the time coordinate t. Then our metric becomes minus 1 minus k over r dt squared plus 1 divided by 1 minus k over r dr squared plus r squared d omega squared. And now this is the Schwarzschild metric if we identify k as 2 times m. And you'll recall from previous lectures, the way this constant is identified as twice the mass is through a Kepler-type experiment. We release a satellite far away and we measure its period and use Kepler's third law to identify this as 2 times the mass. So let me summarize what we found. The most general static, spherically symmetric, solution of the vacuum Einstein equations so those are the Einstein equations with T mu nu equals 0, can be written in the following form. With a suitable choice of coordinates as the Schwarzschild metric. ds squared equals minus 1 minus 2m over r dt squared plus 1 divided by 1 minus 2m over r dr squared plus r squared d omega squared. This is the most general solution, and there's just one free parameter, this mass parameter m. As we've seen, the Schwarzschild metric describes the geometry outside a spherical body of mass m. So in other words, this applies only for values of the areal radius that are greater than some capital R, where capital R would be the areal radius of the surface of the body, or the surface of the star. And as we've seen or discussed, this applies both to the case in which the body itself is static as well as when it's collapsing. Now, if we take the Schwarzschild metric to apply for all R, not just restricted to R greater than some areal radius capital R, then this metric describes a black hole, a spherical black hole of mass m. In the next lecture, I'll talk about black holes and stellar collapse. That's this case and this case. For the rest of this lecture, I want to focus on the case of a static body of mass m. So if this is the body, we know what the geometry is in this exterior region. In this region R greater than R, we have the Schwarzschild geometry. Now we'll turn our attention to the region R less than some capital R and discuss the interior geometry. We'll assume that the interior geometry is static and spherically symmetric. So that tells us, from what we found previously, that the metric can be written as some function gtt of the coordinate r dt squared plus grr of r dr squared plus r squared d omega squared. Now, this problem of solving for the interior geometry of a static spherical star has been worked on by many people over many decades, and what is found is that there's a simpler choice of unknown functions that make the equations later on easier to analyze. So instead of GTT and GRR, let's replace these with the following. We'll replace GTT with an unknown function I'll call capital Phi of r, defined by GTT equals minus e to the 2 phi. And we'll replace this unknown function with m of r, defined by GRR equals 1 divided by 1 minus 2m over r. Now let me warn you, we're used to seeing this combination 1 minus 2m over r a lot in the Schwarzschild geometry, but in that context the m is a constant. In this context, m is a function of r. So with these variables, the metric is minus e to the 2 phi dt squared plus 1 divided by 1 minus 2m over r dr squared plus r squared d omega squared. Now for the matter content inside the star, we'll assume that it's a simple perfect fluid. So we know that the stress energy momentum tensor for a perfect fluid, T mu nu, is equal to the mass density times U mu U nu for the fluid plus the pressure times G mu nu plus U mu U nu over C squared. Now I'm going to set C equal to 1 through most of this calculation. I'll restore the C's at the very end. So let me drop this factor of 1 over C squared. In fact, already in writing the metric this way, I've assumed C is equal to 1. This is really 2 times Newton's constant times the function m of r divided by C squared r. I'm also going to drop the superscripts f here. They're not needed because we won't be considering any other 4 velocities in this calculation. And one other notational change I want to make is I want to change the notation from mu for the mass density to rho. So we'll instead of mu, we'll use the Greek letter rho. And this is the more standard notation for the mass density. And oftentimes it's referred to as an energy density, again keeping with the principle that mass and energy are really the same thing physically. They're just typically measured in different units. So this is still the mass density or energy density. So with these notational changes, our stress energy momentum tensor for the perfect fluid is rho u mu u nu plus p times g mu nu plus u mu u nu. Let me make a general comment about perfect fluids. Perfect fluids are a class of models for matter. So this doesn't represent just a single type of matter. In order to obtain a particular type of matter, we need to specify an equation of state. In other words, we need to specify how the pressure is related to the mass density or energy density. So we need an equation of state which is a relation like telling how P depends on this mass density rho. So when we write down a perfect fluid, a stress energy momentum tensor like this, we really have in mind that we're also specifying a particular equation of state, a relation like P is a function of rho. So in this expression, P is not independent. It actually depends on rho. Now, we've already assumed that the space-time geometry is static and spherically symmetric, so the Killing vector field here is d by dt. So we should impose that on the stress energy momentum tensor for the fluid as well. It should be static and spherically symmetric. So static, spherically symmetric. So in particular, we'll assume that rho depends only on r, and then in turn, since P is determined by rho through an equation of state, then P only depends on r as well. And now we'll also assume that the fluid is at rest in this space-time in the sense that the fluid flow lines line up with the integral curves of the Killing vector field. So in other words, the forward velocity of the fluid is proportional to the Killing vector field d by dt. So that tells us that the components of the forward velocity, only the zero component or the t component, is non-zero. And now using the normalization condition that u inner product with itself has to equal -1, we find that u mu is equal to e to the minus phi. So that's related to the GTT component of the metric, 0, 0, 0. Now given these assumptions, we can write out explicitly the components of the stress energy momentum tensor. They are TT is equal to the mass density times e to the 2 phi. TRR is equal to pressure times 1 minus 2m over r. T theta theta is pressure over r squared, and T phi phi is pressure divided by r squared sine squared theta. And all other components vanish. Remember, P is related to rho by an equation of state, and rho only depends on the coordinate r, and also phi and little m here depend on the coordinate r. So now we're ready to impose the equations of motion. We're ready to impose the Einstein equations as well as the matter equations of motion. And that brings me to a topic that I haven't had a chance to discuss yet. What are the equations of motion for a perfect fluid? So what are the matter equations of motion for a perfect fluid? Well, let me remind you of some things that we have discussed in previous lectures. The stress energy momentum tensor for any matter field will satisfy del mu t mu nu equals 0 when the equations of motion, the matter equations, hold. So, for example, for electromagnetism, del mu t mu nu equals 0 when Maxwell's equations hold. And this is a general statement that just tells us that locally energy and momentum are conserved. So it's just a local statement of energy momentum conservation. The answer to this question for the matter equations for a perfect fluid, it turns out, is del mu t mu nu equals 0. So in this respect, a perfect fluid is unusual in that the matter equations of motion coincide with the statement of local energy momentum conservation. And this isn't true for other matter fields. Again, electromagnetism is a perfect example where the matter equations of motion are Maxwell's equations, and they imply del mu t mu nu equals 0, but they are not identical to del mu t mu nu equals 0. But in the case of the perfect fluid, the full content of the equations of motion is nothing more than just the statement of local energy momentum conservation. Now let's apply these equations of motion to the perfect fluid. We'll assume static spherical symmetry, so the stress energy momentum tensor has these non-zero components, and the metric has this form. The result is the following. The only free index here is nu. When nu is equal to either t, theta, or phi, we just get 0 equals 0. When the index nu is equal to r, we obtain the following equation. P prime, where prime denotes derivative with respect to r, equals minus rho plus p times phi prime. Before I go on, let me correct a mistake I made earlier. The upper TT component of the stress energy momentum tensor for the perfect fluid is rho times e to the minus 2 phi. So there should be a minus sign here. So now this is the result from applying the matter equations of motion to the perfect fluid. Now we can apply the Einstein equations. That's g mu nu equals, setting Newton's constant and the speed of light equal to 1, it's 8 pi t mu nu. Now if we work this out, we see that there's only 4 components of this equation that are non-zero. So the only non-zero components are the TT, RR, theta theta, and phi phi components. But the theta theta and phi phi components of these equations are essentially the same apart from some factor of sine squared theta. So we don't have to worry about the phi phi component. We also don't need to worry about the theta theta component for the same reason that we didn't have to deal with it in solving the vacuum Einstein equations. So the argument is that we know del mu g mu nu is equal to 0. That's the second contracted Bianchi identity. That always holds. And we also know that del mu t mu nu equals 0. That's just the matter equations of motion. So as a result, del mu acting on g mu nu minus 8 pi t mu nu is already satisfied. And if we write this out, for example, for the nu equal r component, we'll see that if the TT and RR components of this equation, the Einstein equation, are satisfied, then the theta theta component is automatically satisfied. So we just have 2 components of the Einstein equation to satisfy, and explicitly they are the TT component, which gives m prime equals 4 pi r squared times rho, and the RR component is phi prime equals m plus 4 pi r cubed times p divided by r times r minus 2m. And now recall our matter equation of motion was p prime equals minus rho plus p times phi prime. So we can use this expression for phi prime on the right-hand side here. And what we obtain is p prime equals minus rho plus p times m plus 4 pi r cubed p divided by r times r minus 2m. This is the famous Tolman-Oppenheimer-Volkoff equation, sometimes just called the TOV equation. So the TOV equation, along with these equations, determine the matter distribution as well as the interior metric for a spherical static star. Unfortunately, these equations can't be solved analytically for any equation of state that's even remotely realistic, but we can solve them pretty easily numerically. Let me indicate how to do that. First, why don't I rewrite these equations inserting all the factors of C and G. And remember, the pressure is given by an equation of state, which we assume has the form P is some function of rho. So the Tolman-Oppenheimer-Volkoff equation can be written as dP d rho times rho prime equals minus Newton's constant times rho plus P over C squared times m plus 4 pi r cubed p over c squared divided by r times r minus 2gm over c squared. And the other equations are m prime equals 4 pi r squared rho and phi prime equals g over c squared times m plus 4 pi r cubed p over c squared divided by r times r minus 2gm over c squared. So these are the complete system of differential equations. They're first order equations for rho, m, and phi. And we integrate these by starting at r equals 0. So we integrate from r equals 0 outward. And we need initial conditions for these integrations. So for rho, we'll just choose whatever value we like. We'll call that rho sub c for the central density. For m, we'll choose the value of m at r equals 0 to be 0. And the reason for that is because notice this factor. When r is equal to 0, the denominator vanishes, and so we need the numerator to vanish as well so that this is not infinite. And of course this term vanishes when r is equal to 0, but then we need m to vanish also. Otherwise, rho prime will be infinite at the origin. Now for phi, we can really choose phi to be anything we like. Notice phi doesn't appear anywhere in these equations except as phi prime right here. So even after we've done the numerical integration, we can always adjust phi by adding an overall constant to it, and we'll still have a solution. So for now, let's just choose phi 0 equal to 0. So we integrate outward from r equals 0 until the pressure drops to 0. And at that point, that signals that we've reached the surface of the star. And let's call the value of r where p drops to 0, let's call it capital R. So now we have the complete interior solution. Defined by rho of r, m of r, and phi of r for r less than capital R. And the full space-time geometry is then given by ds squared, one form for the interior, one form for the exterior. The exterior we know is minus 1 minus 2 capital M over r dt squared plus 1 divided by 1 minus 2 capital M over r dr squared plus r squared d omega squared. So this is the exterior solution where the areal radius is greater than capital R. For the interior solution, we have minus e to the 2 phi. And now let's remember that we can add an arbitrary constant to phi and still have a solution. So let's do that now. Let's call this phi of r, referring to the numerical solution we obtained before, and now we're adding an arbitrary constant to that. dt squared plus 1 divided by 1 minus 2 m of r divided by r dr squared plus r squared d omega squared. And this is the interior solution where r is less than capital R, the surface, areal radius for the surface of the star. So now we need to match the geometry on the inside and the outside. In other words, at r equals r, the geometries should match. Okay, so that tells us if we look at the coefficient of dr squared, that tells us that we need to choose this capital M to equal little m at capital R. So whatever we found for little m at capital R from our numerical integration, we need to choose big M to match that value. And now, equating the coefficients of dt squared, we see that e to the 2 phi at capital R plus this constant must equal 1 minus 2m divided by R divided by capital R. And this tells us what c is. C would be minus the value of phi at R that we obtained from our numerical integration plus 1/2 log of 1 minus 2m over capital R. I'd like to encourage you to spend some time playing with these equations numerically. It's lots of fun, and notice you can just solve these first two equations together and ignore the third if you like, since phi doesn't appear anywhere in here. And for an equation of state, you can choose something simple, for example, a polytropic equation of state. Has the form pressure equals some constant K times the density to a power gamma. And to help you get started, let me give you some numerical values corresponding to a crude model of a neutron star. We have K is around 5.4 times 10 to the third power. That's in SI units, kilogram, meters, seconds, and so forth. The polytropic index, as it's called, is gamma. You can take to be, say, 5/3. And for a central density, you can take this to be a few times 10 to the 18th, again in SI units, so kilogram per cubic meter.